Okay, guys, we are doing the gas laws. So these are the notes for your gas laws. We will go through in two parts. So I'll post one part for this week, and I'll post one part for next week. You will we'll do through. Let's see. From what I'm looking at your notes, we'll do through Gay-Lussac's law, and we will pick up the rest of it next week. So remember, I'm going to post this together. I'll do all of it in one video. You guys will watch what you need, and then you can go into the next part next week. I'll give you a stopping point when we get there. So first thing we got is kinetic theory. So gas contains particles. Of course, we've known this. So gases are these just basically atoms and molecules that are working together. They have perfect elasticity. They are always colliding. The colliding of these cause some sort of pressure. So we know gas pressure, like PSI, the things that we blow up our tires with. You have to have, when you want balloons, you have to have some sort of pressurized gas that's lighter than the air that we have in order for the balloon to float. And volume of gas is primarily empty space particles themselves. So gas pressure is going to be the amount of force applied to an area. So pressure is force divided by area, and we'll go over that in your worksheet. I will have a flipped lesson for all of your worksheets, so that way it will be helpful to be able to do that. So pressure is caused by increased collisions. So the more gas you have in a container, you're going to have more collision between particles. That creates more pressure. So the more force applied in an area creates your pressure. That's what your collision in gases do. So atmospheric pressure is a little bit different. So that results in collisions in the air of molecules with gas and other objects. It decreases at higher altitudes because there's less things going to collide with. Otherwise, it's just colliding with the empty space. And it's very unlikely that you're going to have molecules collide as often higher up. So the lower you go, you're going to have mountains, you're going to have land, people, objects. That creates more atmospheric pressure. So when you go to a thinner altitude, that is going to give you less pressure. So gas pressure is measured in pascals. This is the amount of atmospheric pressure at sea level is going to be 101.3. Remember, we talked about this when we talked about gas and atmospheric pressure last unit. This was the introduction to this, basically. So unit is called pascals. It looks like a kilopascal, but it is called pascal. All right, so pressure in units. Remember, this is what we talked about. You have 1 atmosphere equals this much mercury, this many pascals. That's what you're going to have at all of your atmospheric pressures. So if this is what we have for each one, and we're trying to find how many millimeters of hydrogen or mercury, and how many atmospheres we have here, we have to go in here and figure it out. So what you'll do in order to find out how many atmospheres this particular amount of pascals we have, we have to divide this number by this number, and that gives us how many atmospheres we have. And in order to find our millimeters of mercury, we take a normal PSI and divide that from the number we have, and that's how many millimeters we'll have, because we'll multiply that by 760. And I'll go over more of that when we go through our lesson. because that sounded a lot more complicated than what I meant for it to be, but that's okay. So factors affecting gas pressure are going to be temperature, pressure, so the number of molecules, and volume. These three factors are put into all of our gas laws. So Boyle's law is our first one. So this relates to pressure and volume. So as pressure goes up, your volume is going to decrease. So if we have a higher volume, we're going to have a lower pressure. So that's why we use our line charts. Remember, we use our line graphs in science. We're going way back. This is always talking, Boyle's is talking about a constant temperature. So you always have a constant temperature. Your volume of the gas is going to be inversely proportional to your pressure. So however much volume you have, you'll have less pressure if you have more volume. If you have more pressure, you have less volume of the container. So remember, the pressure of the volume and the pressure is going to be equal to this, depending on whatever the number is. So if we're looking at this, so we have our volume here, we have our atmospheres. So the constant, consider a balloon volume with a 22.4 at 1 atmosphere. If we double that pressure, that means we're taking our volume and cutting it in half. Does that make sense? So whatever we multiply our pressure by, we divide our volume by to get our answer. So that means if the temperature stays the same, your pressure increases, your volume decreases. All right, Charles' law is talking about temperature and volume. So at a constant pressure, volume of a gas is directly proportional to the temperature, so Kelvin. That means what happens with Kelvin, if it goes up, the volume will go up. If the volume goes down, the temperature usually goes down. So your formula is V over T equals V over T. So let's try this. So given our formula, what we do here is we take, let me see if I can find something real quick. I'm going to pause it, and I'm going to see if I can write on the screen. Okay, so I couldn't find what I wanted to find. So what we're going to do is not worry about it now, and we will go over this when I do the flip lesson. So we'll just continue with the notes, and we'll finish later. All right, so Gay-Lussac's law is, so we've talked about temperature and volume. We've talked about volume and pressure. So now we're going to do temperature and pressure. So as temperature goes up, your pressure is going to go up. So we're always talking about Kelvin here. So Kelvin is always your degrees Celsius plus 273. As temperature goes down, your pressure is going to go down. So that is basically the same exact formula. We're just going to replace volume with pressure on top. So you do the same thing. So you got to find Kelvin first, then you plug in everything to your formula, and then after you do that, you find your answer. So if you combine all three gas laws, all right, so this is part 2 of the notes. So once you have finished this practice problem, you can go ahead and be done with the notes for today. Start on Boyle's law first. I'll do a flip lesson for you guys, and then we'll do a flip lesson for Charles' law, and we'll do a flip lesson for Gay-Lussac's law. That will be your work for this week. So you'll have vocab. We'll do 2 of those worksheets, the first half of notes, and then we'll do Gay-Lussac. We'll be due next Wednesday. We'll finish up the notes, and then we'll do your last 2 sections. That's 2 flip lessons. And that'll get us to a review and test on the next week. And then we'll probably have vocab for the next unit on that 3rd week as well. All right, so go ahead and stop it if you are ready to move on to the next thing. I'm going to go ahead and move on to the combination of the gas laws. So if you combine all 3 gas laws, you have this formula. So pressure times volume over temperature, and pressure times volume over temperature. So we have a lot more practice in this one than anything else. So a lot of this will be done with your flipped lessons. And for instance, on this particular one, I'm actually going to set up so I can do your practice problem with you. So hold on, I'll pause it real quick and we'll get to the practice problem. Okay, so as you can see on here, we have our gas laws. So our gas pressure is going to be 745 millimeters of mercury. Our temperature is 15 degrees Celsius, which means we have to turn that into Kelvin. So that'll be 285 Kelvin. And our volume is 30 liters. So what will the new volume be if we increase both our temperature and our pressure? So, all right. So in our first one, we have pressure is going to be 745, and this is millimeters hydrogen, times our volume, which as we see is 30 liters. We divide that by our temperature, which is 285 for our Kelvin. And that is going to equal, or looking for our volume, but we have our temperature. So we increase this by 10 more because we increased it by 10 degrees Celsius. So it'll be by 10. So we have 295 Kelvin. We're looking for our volume. And we have our pressure, which has been increased by 80. So it is now 825. And that is millimeters mercury. All right. So from here, we have to do an algebraic equation. That's all there is to it. So we can find our total by multiplying these two and dividing that. So let's get a calculator real quick. All right, so our answer is 78.4 equals 825 V divided by 295K. So what we have to do is multiply this number by 295 and then divide it all by 825 because you have to get this to just V. And in order to do that, we have to basically multiply it by the inverse of these two numbers. Because when you do that, this gets rid of this gets rid of this. And so now we just have V equals whatever this number is. So we go back to our calculator, we take our answer, multiply it by 295, and then divide it by 825, and that gives us our new volume, which is 28.0 liters, which jives with our laws that we learned, because our law is going to be that as pressure increases, our volume will decrease. Make sense? If it doesn't, we got a couple more practice problems. So moving on. Practice problem number 2. Let me grab my eraser. And we'll set it up again. So we have our setup, which is gas at this many, at 780 millimeters of mercury, and this temperature. So that'll be, again, 288 Kelvin, has a volume of this. What is the new volume? So we set it up the same way. Have our formula for support. So 780 times 15, and then divided by, 18, divided by our Kelvin, which is 285. So what is our new volume at standard pressure? So standard pressure, as we know, is 780 or 760 V, and our standard temperature is going to be 0 degrees Celsius, which is 273 Kelvin. So we set it up the same way. We have 780 times 18 divided by 285 to get our answer. So that means we have 49.2 equals 760 V 273. So again, we just multiply by the inverse. And you'll multiply this number by the inverse times 273 divided by 760. And that's going to equal our volume. Because remember, cancel out, cancel out, cancel out, cancel out. And if we take our answer, multiply it by 273, and then divide by our 760, we get a volume of 17.7. Must have done something wrong there. Because it should be a larger volume based on the fact that our pressure went down. But temperature went down as well. So that makes our volume go down as well. So there we go. There's our mistake. So if temperature goes down, volume is going to go down with it. Make sense? Sorry about that. I made my own mistake. And remember, we're going to have a flip lesson over this too. So if this is confusing now, it is a lot of math. I apologize for you all in advance, but it's okay. We'll get there. So standard temperature and pressure. Remember, 760, 0 degrees Celsius. So that's our. And remember, we always have to do these in Kelvin. So if we include moles in the calculation, we have a new formula. So pressure is always going to be in atmosphere. Volume is going to be in liters. Number of moles is in. R is your gas law constant, and T is your temperature. All right. Go ahead and write that down. Now, let's try a practice problem. Or we can skip it for right now. Nah, let's do it. Let's do the practice problem. All right. So remember, we're going to write down a new formula on our board or on your paper for your instance. So you have P V, so pressure and volume, equals number of moles, your gas law constant, and your temperature. So how many moles of gas are contained at this particular volume, at this much temperature, and this pressure. So we have a little bit of trouble here. So remember, constant is always going to be there. So if we set it up on here, we have pressure first. That's the easiest one. So 750 times our volume. And remember, volume's in liters. So we have to take this and move it to the right 3 in order to get there. So there's our whole system coming in again. So that means we're going to have 0.89 equals in, so that's our number of moles. We have our constant, so it's times point, and remember our constant is 0.0821. 0.0821 times our temperature. We have it in Celsius right now, so we add 273 to it. So we have 294. Because 21 plus 273 is 294. So now we just do the math to get it all together. So let's multiply the first two together. So 750. Oh, I forgot one other thing. So we got to get this to go into our atmosphere. So that means we have to divide this by 760. So let's do that first. 760 or 750 divided by 760 equals 0.98. We'll call it 1.99. So 0.99 times 0.89 that's going to give us our 0.88 equals in times, and we'll do these combined. So 0.0821 times 294 equals 24.1. So now in order to get this over here, we got to divide 24.1 from both sides to get our number of moles. So N equals 0.88 divided by 24.1. And our answer is we have 0.037 moles for this particular problem. See, it's a lot of math. We'll do more practice problems together. We'll skip practice problem 2 for right now. I'll let you guys do that on your own on this. We'll move on to Dalton's law. So in a mixture of gases, the total pressure is the sum of the partial pressure of other gases. So we have to figure out the pressure of each gas, add them all together, and that gives you your total pressure. So for instance, deep sea divers breathe in a mixture of CO2, O2, and helium. So the partial pressure of oxygen is this. If we have the total, we just subtract the other two from it, and that gives you the partial pressure of what oxygen is. So you just take 107.3, subtract R, 87.3, which is the helium, and then subtract our 1.2 of CO2. And that gives us an answer of 18.8 for the partial credit. All right, so coming on, I think this is where we finish for the day. We are at, get 2 more slides. Okay, so characteristics of gases when compressed in a cylinder. Mass stays the same, density stays the same. So those things are the same. This is a gas. Gas particles stay the same as well. But your pressure is going to increase as your volume decreases. So this is the same thing that we talked about with the laws before. And the distance between the molecules decreases as well. So that is what actually increases the pressure. Because if we're decreasing the space that it's in, we're having a lot of distance between them, increasing the pressure and the amount of collisions we have between the molecules. So an area of high pressure is always going to be a diffusion of gas. So area from high to a low. Remember, water goes the path of least resistance. So liquid will do that. So does gas. Gas always goes the path of least resistance. So area of high pressure to low pressure. That's diffusion. All right. So that's it. I will post your flip lesson for what the practice problems we just did. We'll do some more flip lesson later. Good luck with all this. I know it's a lot of math. You'll be all right. It's just doing your different algebraic equations. It maybe take a couple steps, but it's not too hard. All right. Have a good week. Thus ends part 2. Please email me if any questions. If you'd like to set up a one-on-one lesson, let me know. Talk to you later.